Okay, thanks a lot for this invitation and this opportunity to give this talk. And thanks also for accommodating the time because, it's North America with 6 hours difference. Okay, so I'm going to talk about something which I find is quite interesting in the context of quantum gravity and cosmology, and somehow how quantum gravity effects might have real physical implications for cosmology that we observe in the sky today. And it's going to be based on these papers that I mentioned here. Okay, so I'm going to talk about more specifically about the swampland as the title suggested. So what is the swampland? And let me be very heuristic here. The swampland can be defined as this set of apparently consistent effective field theories, which cannot be completed into a quantum theory of gravity in the ultraviolet. So that's how it's defined, especially by Palti here from a review from 2018. And what does it mean? So of course, this came about specifically in the context of string theory, and it should be seen as a complement to the string landscape. So the idea is that that string theory might lead to a very large landscape of low energy effective field theories, but there is an even larger, much larger swampland of effective field theories which cannot come from string theory. So you can have all these lots of EFTs which can descend from string theory, but there can be a lot of other EFTs which do not form part of this landscape, and those are these inconsistent EFTs. So these EFTs from the low energy point of view look perfectly consistent, but when you try to integrate them, when you try to complete them into some UV theory, then there's some problems. So the idea more specifically is that there are some concrete principles which must be obeyed to avoid being in the swampland. So you need to obey some conditions to be able to be in the landscape and not the swampland. So by the way, I don't know if I will see if anyone raises the hand. So if someone has a question, please interrupt me. So for example, there's this weak gravity conjecture, which says that gravity is the weakest force, and there's this distance conjecture and also the de Sitter conjecture. So I will mainly talk about this de Sitter conjecture, which essentially rules out metastable de Sitter spacetimes in string theory. Okay, so this is a very powerful proposal to constrain the space of all low energy FTs. So whether you believe in it or not, at least given the swampland, like let's say for a second that we take it to be true, then this would be a very powerful way to constrain the space of all low energy FTs. Remember, for example, when you want to do some model building for inflation, you can start with some low energy effective field theory with any potential, with no constraints on the potential, as long as, let's say, it's renormalizable or something like this. But now there is some additional conditions which this potential and things like this must obey. So this has a lot of similarities with the early days of quantum mechanics. You are sort of inventing quantization rules. There's a deeper structure underneath which we don't see yet, but we are inventing more and more structure as we go along, and we see different parts of this underlying theory in these conjectures. Okay, so where's the confrontation? And for that, of course, we have to say, why do we need this space? And this everyone knows that we require at least 2 stages of accelerated expansion. One is this inflationary era, typically assumed in the early universe, and the dark energy era. So, of course, these are not the only way to explain data right now. There are alternatives to inflation, alternatives to dark energy, alternatives to lambda CDM. But the simplest solution, it just posits this. The simplest solution is that you have de Sitter and this quasi de Sitter phase of inflation and lambda CDM, which fits data perfectly. So we should go for the simplest option, of course, from the observational point of view. But then, as I just said, the de Sitter conjecture rules out de Sitter space. So then you can't have this. Well, at least definitely not lambda CDM. Well, the question then is, why should a cosmologist bother about this? Why should someone is requesting something? Should I allow? I don't know. There's a request for something on my screen which popped up. Anyway, I'm not doing anything with that. Okay, so why should the cosmologist be at all bothered about the swampland? Because if a theory explains data, that should be enough. Well, the reason is because inflation by itself is not complete. Of course, we need to understand the origin of inflation, of the inflaton field, and what should be the initial conditions should typically come from some quantum gravity theory. Everyone more or less agrees upon this. And also for the dark energy, we have to resort typically to some anthropic solution for the cosmological constant problem if you believe in it. And then again, you have to depend on some sort of multiverse or some quantum gravity argument. I mean, the point here is that let's forget dark energy for now and let's go to inflation. For sure, it is important that we understand how the inflation begins, what are the initial conditions for it. And for that, you have to resort to some quantum gravity theory. And you can't have it both ways. You can't say, I require string theory to explain inflation. Let's say if you believe in string theory, and then say, I won't take other predictions into account. If you want to have a string theoretic explanation of why inflation begins, you must also take into account this kind of bad prediction that, there's a lot of the swampland out there. So the goal of this talk is to, address 3 points as quickly as possible and as briefly as possible, which is, how trustworthy is this de Sitter conjecture, more generally the swampland, but the de Sitter is what I'm going to talk about. And if this is somewhat trustworthy, this is a very good thing, because this just tells you that the standard cosmological paradigms needs to be urgently revisited. You can't have this anything goes anymore in cosmological model building, because there's this zoo of inflationary models, for example, with different potentials that would be ruled out. Many of them would be ruled out. And then finally, we have to answer the question, like, is there some way to resurrect de Sitter space from the swampland, or some version of de Sitter space? And my own answer to that would be like, yes, maybe some non-perturbative quantum effects would allow you to do that. If I have time, I'll get to that. Anyway, so the interesting part, if you fall asleep just after the slide, is that there are some consistency conditions which are appearing from some UV theory, which are affecting and severely constraining physics that we know right now. So this is exactly going against the grain of, we can never see any effects of UV physics or quantum gravity at all in physics today. Well, this is going against that and somewhat in line with what Aurelia was just now suggesting in the context of black holes. Okay, so let me just start with inflation and the swamplands. And the idea is that, there's this, as I mentioned, this zoo of inflation and late time cosmology models, and even this precision cosmological data is not sufficient to differentiate between most of them. And particularly for the early universe inflation models, the swampland criteria puts very severe constraints on this plethora of these models. And the refined de Sitter conjecture and even more recently, this Transplanckian censorship conjecture, the TCC, points towards a specific type of models, which are this hilltop inflation. I haven't explained what the TCC is. I'll come to that in a while. Well, but the initial suggestions were that all single field models of inflation are ruled out by the swampland, and since then there has been different approaches rescuing single field models out of inflation. And the one I'm going to talk about is having this non-Bunch Davies initial state, and I'll explain why I think this is a solution which has greater significance than just rescuing inflation. Single field inflation, because somehow this, I feel, and I'll argue that non-Bunch Davies state would be more natural than the Bunch Davies one for inflation for several reasons. So as you notice, I'm starting with what are the effects of the swampland, and then I will come to whether there is enough evidence to believe in the swampland to begin with. That will be the second section of the talk. Okay, so what are this de Sitter conjecture? And so S1 here is the distance conjecture. So for our purposes, this just says that in Planck units, the field should not have excursions, should have less than order 1 number excursions. So the field should not have super Planckian excursions. This is very reasonable. People knew this for a very long time, and that's why, like, large field inflationary models were always like fine-tuned so that delta phi doesn't go bigger than mass Planck. But the second one is the new one, and this is the de Sitter conjecture, which says that the V prime over V, V is the scalar potential, let's say, has to be greater than some order 1 number when V is, of course, positive. And this just rules out all metastable de Sitter. And then there was a refinement to it, and the refined de Sitter conjecture just says that either this first condition is true, or if this is not true and V prime over V is small, then better V double prime over V must be large. So in other words, there must be some tachyonic directions. So, and again, this has to be some order 1 number. So these order 1 numbers are not specified, but is there a question? Okay, no. So naively, this is obviously in serious conflict with usual slow roll definitions, because I mean, one can see this very quickly, because the epsilon can be defined in terms of this C, this order 1 number I just said, and then this epsilon would have to be order 1, which is of course saying that there can obviously be no inflation or any quasi-de Sitter spacetime. But of course, this is not true, because C, I just said, has to be some order 1 number. This doesn't have to be exactly 1. And for example, as was pointed out very early on, after these conjectures came out, this can be parametric, and C can be 0.5, for example. But the real problem is something else. The real problem is that we have an upper bound on the tensor to scalar ratio. And this tells us, and then there's this consistency relation between single field, for single field inflationary models. So inverting this relation or using this relation for R, we can get an upper bound on the epsilon, or this, which can be related to this V prime over V, and then that tells you that C has to be less than 0.1. So of course one can argue it's 0.1 an order 1 number, but the real problem is that, I mean, if we don't observe R in the future, we have to keep doing this fine tuning. And then C has to be less than, let's say, 0.01 and so on. And then this is going exactly against the grain of the Swampland, which is to say that, you want to avoid this fine tuning in the string landscape. So somehow, if we have to rescue single field inflation, we have to violate this consistency relation written in red here. And to do that, there are different ways. Of course, we can go to multi-field models. We can have warm inflation, which has some new degree of freedom in terms of radiation bath. Or we can just, so somehow we have to go beyond this vanilla slow roll single clock model of inflation. And the one, as I mentioned, I would choose is to have a non-bunch Davies state for the fluctuations. So there's no additional field for the duration of inflation. There's just a non-bunch Davies component to the scalar and tensor fluctuations, let's say. How does this work? So you see, for a generic excited state, this is what the power spectrum looks like for the scalar modes and the tensor modes. So the red terms are the ones that are modifications because of the non-bunch Davies initial state. And these alpha k, s, and t in principle can be different. Of course, there's only one free parameter because there's some phases which are irrelevant, and then there's this normalization condition which they must satisfy. Of course, there's also back reaction constraints which tell you how fast this beta function must fall off to 0 for large k. But you can immediately see that now this consistency relation is modified, and now R is equal to some 16 epsilon gamma, where gamma is defined as this ratio of these modification factors. So of course, if gamma is less than 1 now, one can have R is small, even though epsilon is not that small. So, we haven't observed R, we have bounds on R. So this, if we change the consistency relation, R can be small, and even then epsilon can be large. Of course, there's two ways to achieve this. You can either make this denominator small, the numerator small, or the denominator large. It just turns out that if you make the numerator large, so if you make the denominator large, that just means that you're modifying the scalar spectrum too much, and it leads to some very high, unacceptably high values for the local non-Gaussianity. And we know we also have bounds on non-Gaussianity, so this cannot be a possible way out. And the way out would be to make this tensor modes, this numerator small. It can be made small even with large beta, because there's a relative phase between alpha and beta, so that this can still be made small. And that's how you rescue sort of inflation out of this de Sitter conjecture. Okay, why do I want to advertise for non-bunch Davies states? Well, the point is, let's ask this question differently. Even if there is no classical potential with some stringy corrections which allows for metastable de Sitter, can radiative loop corrections not lead you out of the Swampland? And this question was answered by Ulf Danielsson recently, saying no, you can't. Radiative corrections always make things worse, and that's because if you calculate the one loop Coleman-Weinberg potential, you find that for an inflation field, you find that the de Sitter invariant term is de Sitter invariant only when one chooses the bunch Davies vacuum. But how natural is it to assume the bunch Davies vacuum? And this is the debate that has gone on for a very long time, between people like Polyakov and Susskind and so on. And let's try to understand this the way I understand this, which is, let's take a mode expansion. So what is the bunch Davies vacuum? So we do these mode expansions for the fluctuations. For a given k, let's trace the mode back in time. So its physical wavelength keeps getting blue shifted, so that at some point its wavelength will be much smaller than the Hubble scale, and the mode forgets that it is in de Sitter space or curved space, and it feels like it's in flat space, and we choose the unique Minkowski vacuum for it. And the point is, if we choose this eta naught when inflation begins to be at -infinity, you can take any mode that you want. You just have to blue shift it back enough so that it is much smaller than horizon scale. And once it's much smaller, it feels like it's in flat space, and you can choose the bunch Davies vacuum for all these modes. But the problem is that you should not blue shift a mode beyond the cutoff of any theory. And we know inflation is an effective field theory in curved spacetimes. It must have a cutoff. It must have some quantum gravity cutoff, let's say given by mass Planck. So we shouldn't blue shift a mode beyond mass Planck. And this would be the main argument for TCC later on. So the other way to deal with this then, if we want to impose a cutoff, is that we would have to parameterize our ignorance about what is happening before inflation somehow in the initial state. So we just say that we don't understand what's happening before inflation. And of course, for specific cases like two field models, you can integrate out the heavy field, or for some radiation era before inflation, you can see what happens. And in all these cases, you get a non-Bunch-Davies state resulting out of this as the initial state for inflation. And that's bad, because if you have a non-Bunch-Davies state, that really talks about this quantum Swampland. So now, even if you have some classical solution which obeys de Sitter, because you have a non-Bunch-Davies state, the one-loop effective potential will not obey de Sitter symmetries anymore. So in some sense, you would always end up in this Swampland, and so you won't have an eternal de Sitter space anymore. And one might argue that, is there not some de Sitter no-hair theorem, like the Bunch-Davies is an attractor, some quantum attractor? And the answer to that is, for short-lived inflation, so if inflation starts at some finite eta naught, and I will quantify what I mean by short-lived later on, then this is not true. You do not have, there is no hair theorem. Bunch-Davies is not an attractor. It requires at least a lot more E-folds to become an attractor. So there's some similar results about dark energy. Like, so if lambda CDM is ruled out, what about quintessence models? That's the ideal one. Well, quintessence models have a double fine-tuning problem. Like V is very small, and we know that delta V or V prime is also very small for quintessence models. So if cosmology constant has a single fine-tuning, then quintessence models have double fine-tuning. But that's good because, well, as I mentioned, and the second one comes from these observational constraints on the equation of state. But the point is that the Swampland naturally solves this problem because it relates V prime to V. V prime over V is some order 1 number. So if V is small, then V prime also has to be small, of the same order. So then it's ideal to go to quintessence. But on closer inspection, it's found to be in conflict with the Swampland as well, once observational constraints are taken into account, and this was shown in this paper. And in fact, in a subsequent paper, it was shown by Lavinia, Robert, and others that almost all of Horndeski theories compatible with current observational bounds in dark energy have been found to be in the Swampland. So if I impose this de Sitter conjecture, then almost all of these theories are in the Swampland. I will talk of an exception again to rescue dark energy from the Swampland, which is this cubic Galilean model. This has not been ruled out by ISW measurements and so on, and or multi-messenger astronomy. And once again, if I impose the de Sitter conjecture on this model, on this potential, it is not ruled out by current data. So the thing on the left is the plots for quintessence, whereas on the right is the one for the Galilean model. And the point is, if you just notice one thing, these cosmological histories, these solid curves are the bounds coming from current data. And if you look at the cosmological history, they are shifted somewhat downwards in the right plot, and that's what saves them. So you can have this lambda, which is this C I referred to earlier, to be order 1, and yet these are all consistent with data currently. Okay, so let me quickly talk about what does the Swampland help, and I believe this is one of the nicest predictions out of the Swampland, that it rules out stochastic eternal inflation. So stochastic eternal inflation is often invoked to dynamically populate the string multiverse, and to invoke this to answer this question of the cosmological constant problem with some anthropic principle. But the point is, for stochastic eternal inflation, quantum fluctuations have to be strong enough to balance classical field motion, so that the field can now wants to drift downwards due to classical motion, but it can also go up because of quantum fluctuations. And the extra inflation cannot entirely be for free. And because there is this competition between classical and quantum motion and classical drift, these high energy modes have to be consistently redshifted into the low energy theory, even if the field is pinned at some point on the potential, as it has to be for eternal inflation. And what we found with Sarah Shandera recently is that if for stochastic eternal inflation to be under perturbative control, so it means that if you want to have the loop corrections to the inflaton propagator and things like that coming from the bispectrum and trispectrum to be under control, to be under perturbative control, you can never have eternal inflation once given this Swampland conjectures. And quite independently, similar results were achieved using the Fokker-Planck equation by Robert Brandenberger and collaborators, and also by Tom Rudelius, who actually turned this around to say that perhaps the de Sitter conjecture is a no eternal inflation conjecture in disguise. So that's like the physical reasoning behind the de Sitter conjecture. I won't go into details, but I'm happy to answer questions later on. Okay, so now let's come to the more serious point. Why should we believe in all this? Why should cosmologists take the Swampland conjecture seriously at all? Okay, first of all, in the concept of string theory, they can be derived from the de Sitter conjecture. and the usual covariant entropy bound. And you might just say that this is cheating because I'm now saying believe in some other conjecture from string theory instead of believing in the de Sitter conjecture. That's not quite true because the distance conjecture has been much more rigorously tested in string theory. And it was shown that, then assuming this distance conjecture, you can derive the de Sitter conjecture. I won't go into the derivation, but this was shown in this paper from 2019. I'm, again, happy to go into details if anyone has questions later on. But there are other evidence against de Sitter spacetime for a long time as well. So again, in the context of string theory, there's an enormous difficulty of constructing metastable de Sitter vacua, which people knew for a very long time, in spite of solutions like KKLT and LVS scenarios. All of those solutions have been found to have some problems. In fact, even without quite going into string theory, the classical symmetries of de Sitter have been shown to be inconsistent with finite entropy. And if the classical symmetries of de Sitter are eternal and they never break, then you never can have an finite entropy for de Sitter space. And this was shown by Susskind and others, which points to the fact that the de Sitter symmetries must break after some time. And this led to other work by Diwali, again, not in the context of string theory, but more generally, that there is a quantum breaking time for de Sitter space. And in fact, recently there's some work by Tirok, Feldbruch, and Lenners, which say that if you choose this very famous Hartle-Hawking wave function, which also gives a quantum completion of de Sitter spacetime, that runs into some problems as well. So it seems that there are some different quantum gravity approaches which are finding some problems with de Sitter spacetime. And now I'll talk of two other possibilities, which obstructions to de Sitter spacetime coming from EFT arguments. The first one is due to Motola and Polyakov for a long time. When you do QFT on de Sitter spacetime, you find some instabilities, and I won't go in details into that. And the second one is the Transplanckian censorship conjecture, which puts an upper bound on the lifetime of any metastable de Sitter spacetime. So I have 5 minutes.
So formally, yes. Yeah.
Okay. Okay, good.
But we can take. We already. According to the schedule, we're already starting the coffee break, but you started a bit later. I think just 5 minutes later, so we can take time from your question time. Okay, is that fine for you?
Yeah, that's fine. That's fine. Yeah.
Okay.
5 minutes is good. So let's come to this TCC, or this Transplanckian censorship conjecture. So of course, one of the crowning glories of inflation is that it explains the origin of observed macroscopic density perturbations in quantum vacuum fluctuations. That's one of the best predictions of inflation, and it worked out. But the point is, if you look again, this is this argument which I gave earlier very briefly. If you look at a physical wavelength in the sky today of a classical perturbation mode, and then blue shifted backwards, due to the expansion of space-time, one might end up with a physical wavelength that is much smaller than Planck length. And this would happen, of course, if you have lots of inflation, then we can keep it blue shifting it backwards, and then finally it might end up with some wavelength, physical wavelength smaller than Planck length. And this was known as the Transplanckian problem. As I mentioned, then this would mean that Transplanckian quantum fluctuations are the sources or the seeds for macroscopic perturbations that we observe today. There's something very wrong with that, because inflation can only be valid until energy ranges up to the Planck scale and not beyond it. It cannot exist as an EFT beyond Planck scales, no matter what is your underlying quantum gravity theory. Almost everyone agrees with this. Now, one would typically assume that why does Wilsonian EFT doesn't work? Why can't we put a knife cutoff? And that doesn't work because of the nature of these expanding backgrounds. And I cannot, again, go into details, but that there is some non-unitary evolution which results from a time-dependent Hilbert space, because of the degrees of freedom keeps increasing. This was pointed out by Weiss and Tate Jacobson in very nice papers. So the TCC is saying that these Transplanckian quantum fluctuations, maybe they're there, maybe they get redshifted a bit, but they should never cross the Hubble horizon. And as long as they don't cross the Hubble horizon, they would never decohere and be part of this classical perturbation mode. So we will never observe them. So that's the idea of the TCC, that we must have inflation bounded from above, by the number of e-folds of inflation bounded from above, such that these Transplanckian quantum fluctuations never get to decohere and become classical. So this is the picture. So these blue lines show you density perturbation. So let's take the first blue line on the right here, if you can see my cursor. This is the characteristic of the size on the sky today. And you blue shift it backward, it must originate from inside the Hubble horizon at the beginning of inflation. And this is just saying that inflation must explain classical perturbations as quantum fluctuations. And on the other hand, there's this upper bound now, which tells you that, you know, a Planck length mode should never cross the Hubble horizon. So now you know how much, what the hierarchy, the number of e-folds of inflation must satisfy to both explain density perturbations as quantum fluctuations and also not to have transplancking fluctuations leak out and be part of our observations. And this results in something like this. So TCC prohibits the upper bound on the number of e-folds like this. And as I mentioned, there is a lower bound coming from the fact that inflation must explain scales that we see today as being in causal contact in the early universe. And if I use these two bounds, if I use this hierarchy, I find that the energy scale of inflation is bounded from above by a very small scale. And then this implies, using the observed scalar power spectrum, that epsilon has to be very small, and the tensor to scalar ratio also has to be very, very small. And if I now use the spectral tilt, this tells me that, you know, eta has to be somewhat large. Well, eta is still 0.02, but if you compare it to epsilon, it's large. And this is nice because this gels nicely with the Swampland de Sitter conjecture, which told you that, you know, when v prime over v is very, very small, which is the case here, then v double prime over v must be large, which is again the case here. So that's nice. That's quite independently verifying the de Sitter conjecture. Strict bounds on R are not easy to evade. So one point of view pointed out by Robert and Kumrun and others was that, you know, this is part of the predictions of inflation. You can never have large R. If you have large R, the theory is not inflation. Or as I showed later on, that you can invoke alternate mechanism for production of primordial tensor modes, and then the TCC can be made compatible with R, with an upper bound on R such as this. Of course, you still need extreme fine tuning because epsilon is very small, which means that, you know, the initial velocity for the inflaton has to be very small. But how can we explain that? And that can be explained by something like, let's say, the tunneling wave function, so which hints at some non-perturbative quantum gravity effect coming to the rescue. And let me just take 2 more minutes to, so this is not a problem for other alternative early universe scenarios. Let's just take 2 more minutes to say what is the relation to the Swampland. I'll just give you the brief overview, which is that the TCC, starting from the TCC, you can derive the de Sitter conjecture with a specific number for this order 1 number, which is given by this. The TCC itself, as I showed, can be derived from a distance conjecture, and as I mentioned, that has been more rigorously verified in string theory. And this gives another route of deriving the de Sitter conjecture from the distance conjecture, a different route than the one I mentioned earlier. And as I mentioned earlier, the TCC just implies that one must, even if there is metastable de Sitter vacua that is compatible with the Swampland, they must be short-lived with some lifetime given such as this. And this is typically inconsistent with everything that people have found so far in string theory. So how can we rescue this with non-perturbative quantum correction? This should be my last slide, more or less. Well, you can't have de Sitter vacua, as I pointed out, unless they're very short-lived, and it's very difficult to create vacua like that because the lifetime of de Sitter vacua is typically controlled by the Coleman-DeLuce instantons. And the only way to do it is to treat de Sitter as a coherent state over some Minkowski vacua. So you have some Minkowski vacua, that's perfectly fine. Maybe some supersymmetric Minkowski vacua, maybe some warped Minkowski vacua from string theory. And then there is some coherent state description which leads to some de Sitter space, an emergent de Sitter space. And right now we are working on this, and this solves the Transplanckian problem. This gives you a finite entropy of de Sitter spacetime as, evading the objections of Susskind and so on. And also this leads to a Swampland consistent de Sitter realization. I won't go into my outside string theory example with loop quantum gravity, which was just mentioning this point that, the Bunch-Davies can come out, the natural quantum completion of Bunch-Davies can come from the Hartle-Hawking wave function, but recently Neil Turok and Jean-Luc Lenners and collaborators showed that they have some problems when you consider perturbations. The perturbations are runaway type. But then if you include some loop quantum gravity corrections, you can correct for that because of some very non-perturbative effect of signature change. And that leads to having the correct sign with some Gaussian fluctuations, and you can again have some Bunch-Davies, some usual de Sitter spacetime with some quantum completion without any problems. But you need some non-perturbative quantum corrections. And I will just leave this final slide here if anyone has questions. Thanks.
Thank you, Sudha. Thank you, Sudha, a lot.
Thanks.
Let's thank the speaker. So I think we have time just for one short question. Any question? Laura, yes, please.
Thank you for your talk. Can you please go back to the slide where you say that it is possible to have R like less than 10⁻³ with some mechanism? So I wanted to ask. If you can comment on that.
Yeah. So so you mean this, right, for the TCC?
Yeah.
Yeah. So this is just saying that, okay, I'm cheating a little bit here. So the way I showed that this is okay is if you have, again, some non-bunch Davies state for the tensor perturbations now. Now, you can ask me, how do you get non-bunch Davies for the tensor perturbations? And my answer to you would be rather vague. The only way I know of generating some non-bunch Davies state for tensor perturbations would be to go to some theory like Hoshava-Lifshitz theory or some other UV theory like loop quantum gravity. And those can lead to some non-bunch Davies state for tensor perturbations as well. The usual integrating out of scalar fields or warm inflation and things like this do not lead to such states. It leads to states for non-bunch Davies for the scalar perturbations. For the tensor perturbations, which is crucial for this argument, we need to go to something like Hoshava-Lifshitz or loop quantum gravity or something like this.
Okay, thanks.